Okay, so our last speaker for this session is Charles Kankelborg, who is a physics professor at Montana State University, and the title of his talk is On the Statistical Plausibility of Divine Providence.
Thanks, Arnold. So when we speak of divine providence, what we're talking about is God's continuing activity in the world. And I really appreciate having the chance to go after Robert and Roger. They did a wonderful job of really introducing this topic and getting us all thinking about it. There are many examples in Scripture of God being active in the world. Two of my favorites are the book of Esther, in which God's name is never mentioned, and we're left to try to discern for ourselves whether and when God is acting in that story. And then much further along in the New Testament, Jesus calming the storm. We have all seen storms. We all know that every storm comes to an end. Usually it's kind of gradual, but it can be abrupt. But we're not used to seeing people telling the storm to end and having it just end just like that. And so that's why that story is so special. I would assert that if you take Christianity and subtract the idea of God's continuing action in the universe, subtract providence from it, in other words, what you're left with is deism. And I don't think that's where we want to go. I find it helpful to follow the categories that others have set up in trying to understand what providence is. And the three categories are general providence, which is ordinary events that result from natural causes, that flow the way that they normally do. Really, this is the subject of our work as scientists, right? We try to understand that natural order that God set up. Then there is special providence, in which events are still attributable to natural causes, but they occur in a special time or place or context. You might put Jesus calming the storm in that category because of its particular timing in relation to Jesus telling it to stop. Or you might put that act in the realm of extraordinary providence, that is, miracles, events which are not naturally explainable. The resurrection maybe stands out as an example of something that, well, I really don't see how that could possibly be a natural thing. But maybe I'm wrong. You can see, I think, that there's some squishiness in these definitions, right? It's not always easy to categorize. Nevertheless, I think the categories are helpful. Special providence, I would say, is important because we also, as Christians, are encouraged to intercede for one another, right? To pray for one another. And if my intercession for you or yours for me were based on the notion that we have to ask for a miracle, it would be rather discouraging, wouldn't it? Because miracles are few and far between, right? Even in the pages of Scripture, they're few and far between. And so if we were to rely on that alone for God's intervention in our lives or God's activity in our lives, then we would feel, I think, discouraged. It's better to be able to think that God acts every day in our lives in some fashion, whether we can understand it or not. So I'm going to focus particularly on special providence. I apologize for the funny fonts, by the way. This is just something that happened when we moved the presentation onto a Windows system, and I thought I'd embedded the fonts, and well, I don't know. I suppose it's God in his providence trying to show me some humility. But anyway, there's this wonderful idea that Polkinghorne explored, and he's not the only one to explore it, to try to help us to understand how to put together providence with a scientific understanding of the universe. So the notion that since our universe is comprised of both cause and effect, that is, laws of nature, but also a certain amount of randomness or unpredictability, those two things are put together. Perhaps the random bits are a kind of causal joint through which new information flows into the universe, and that this may make room for special providence. So one way of thinking about that is to suppose that the microscopic randomness associated with quantum mechanics is an ontological, that is a sort of inherent randomness, and that chaotic systems, which are the key notion there is sensitivity to initial conditions. A chaotic system, you give a little tiny perturbation, and a little while later, it amplifies exponentially to a very large outcome, often called the butterfly effect. Well, if you put those two things together, then there's that microscopic source of information, and then there's its amplification to really consequential scales. Now, many objections have been raised to this idea of a causal joint, and I think many of those come down to a question of theodicy. That is, it's a little scary to make God responsible for everything on a day-to-day basis because so many bad things happen, right? And that's not a question that I can answer in a 20-minute talk, so I'm going to avoid it. But nevertheless, it's good to acknowledge that that question exists. Nevertheless, in my view, special providence is essential to Christian theology. We really dare not throw it out. And so what I'm going to try to do today is to subject Polkinghorne's hypothesis to a bit of a hypothesis test to the extent that I'm able, and try to convince you that I've supported it to some degree. So there are several counter-arguments that I specifically want to try to refute with what I've done. One is theological. It's the implication that if God has to come in and make corrections or course changes, then it seems to imply that God's laws are inadequate to accomplish his own purposes. That would be worrisome, right? We don't want God fighting against the creation. And then there are a couple of more technical issues. One, that random processes may not offer enough freedom to support providence. Not everything is random, after all. And a lot of random things, like the random movements of the air molecules in this room, are highly unlikely to give rise to a wind rushing through here or something like that, right? There's statistical averaging that sort of suppresses that and keeps it at a low level where it's not consequential. And along with that, there's the idea that random fluctuations are often trapped at these microscopic scales. So those technical issues deserve a quantitative investigation. And I got to thinking about water waves, storm waves in particular, and there's this really kind of tragic story about the SS Edmund Fitzgerald, which was lost with all hands on Lake Superior in a terrible storm on 10th of November, 1975. You may have heard the famous ballad by Gordon Lightfoot about this, which has been ringing in my head now for several months as I've been thinking about this topic. So I'm going to just take the hypothesis as given that the Fitzgerald was sunk by rogue waves. That's not proved. There's some evidence in that direction. But let's just, for the sake of argument, take it that there was a big wave that rose up out of the sea and sunk this freighter. And my question that I'm going to try to answer is, could random processes afford sufficient freedom for God to determine the conditions encountered by vessels in such a storm? So, being a physicist, I, of course, made a two-dimensional wave model. And it's a linear model because that's the kind of physics that's easy to do on a computer pretty fast. And this model covers only a 10-kilometer square portion of that large body of water. The conditions are modeled on the particular storm in which Edmund Fitzgerald was lost. The waves with a crest height over 9 meters in this context would be out in the tails of the distribution. They would be considered rogue waves. And those would occur with maybe 5% probability per hour in any given location. So a particular vessel in a several-hour storm probably wouldn't encounter a rogue wave, but it might. There is deterministic evolution in the model, the phases of the waves being advanced in time. But then I've also inserted a bit of random phase noise, a bit of wobble in the waves. And the reason for that is that it's not a closed system. There's wind driving going on here. And so I have to have a little bit of stochastic input, but that is small compared to the deterministic component of the model, and it accumulates only gradually with time. So this is not then a chaotic model. There's no amplification going on. I've also made a little tweak in which I have amplified the largest waves in a nonlinear fashion, because if I don't do that, then the statistics of the rogue waves are incorrect and don't match observations. So I've done that only as much as necessary to match actual observations of storm waves. So with this model, I'll demonstrate the evolution of a specified state from an arbitrary state. That is to say, I'll start with whatever I'm given with a random number generator. I'll advance it forward in time, but I will sort of splice in a specified state by the end of the simulation and show how that can be done organically without altering any of the dynamics or statistical rules of the model. The model uses a two-dimensional power spectrum. You can view this as just a map. So the red and blue bit here is where most of the wave power is. These are waves that are moving to the southeast because of a northwest wind, and they have a certain range of speeds and wavelengths. And the blue contour here encompasses almost all of the wave energy in the model. Every point on this graph is a wave mode, that is a particular direction and wavelength, or a particular direction and frequency. And so that point right there is a mode. And what does that mode look like? Well, it looks like that. It looks like waves of a particular wavelength moving in a particular direction. And so the model as a whole is just a superposition of many of these modes. There are at least 10,000 that are statistically important. So the model moves forward, as I said, by propagating these phases of the waves and also inserting a little bit of random phase noise as it moves along. All right, so what I'm going to do now is I'll show a very brief little movie that's zoomed into a 2x2 kilometer portion of the simulation, and you will see rogue waves that have just occurred, just popped up naturally in the model, so that you can get an idea of what the character of them is. You'll see little spotlights that highlight them so it makes it easier to find them. And you may notice within the spotlights, little red contours. Those are where the crest has gone above 9 meters. And so those are, by definition, rogues. Besides being very localized in space, these things are localized in time. This rather atypical trace of time at a particular position shows a rogue wave. I say atypical because most positions would not see one, but you can see that it occurs in just one little section here where there are three that come together. These are often called three sisters in the language of seamen. So here is a whole model run, 15 minutes long on a 10 kilometer square. You see lots of little rogues popping up, highlighted by the spotlights. They occur too fast for me to point at them with the pointer because I'm running a lot faster than real time. And we just watch that for a minute. And as we reach the end of the simulation, we're going to zoom in. We're going to zoom in right in on the center. And now you see the very last event of the simulation, a rogue wave that occurs right at the origin of the coordinate system at 0, 0, exactly at the end of the simulation. What a coincidence. Except it's not a coincidence, I put it there. How did I put it there? I claim that I did it in a way that's completely consistent with the statistics of the model. There's nothing other than its unusual position that would give it away. So how did I do that? Here what we're seeing in the upper trace, there are two graphs of phase as a function of time. I'm looking at just the phase of a single mode to show how this works. And the blue trace going here is showing the phase of what I call timeline 1. So this is starting from a given initial condition, which I have not manipulated, moving forward in time with a mainly deterministic but slightly randomized phase as a function of time. So phase sweeps from plus pi to minus pi and starts again at plus pi, does it over and over and over again. And that's just the progress of this wave. Well, so then there is a red timeline that looks rather different. The red timeline ends in the state where I want it to end. And in some cases, depending on which mode I'm looking at, it may be very different between the red mode and the blue mode in the end. And the thing is that because the simulation is long enough, and because both of these things, both timeline 1 and timeline 2 have their own independent noise, there are places where the phase just happens to correspond. So right in here, there's a place where that happens. Right here, there's a place where that happens. And in this case, my algorithm has chosen this time at t plus 8 minutes approximately as the place where there's the best correspondence between the phase of timeline 1 and timeline 2 for this particular mode. And so that's where it makes a splice. The resulting trace is the green one, which agrees with the blue on the left and the red on the right and makes a seamless joint between the two. So consequently, we are left with a deterministic, mostly deterministic trajectory with a little bit of phase noise that just happens to end up where I want it to, even though every bit of phase noise is randomly drawn from the same distribution. So you might ask, how flexible is such an algorithm? I used it to really just affect a tiny part of my simulation before. And so I'm going to start with that end state as the beginning state of another simulation, again, 15 minutes in length. And by the way, the 15-minute coherence time that limits how long it takes for me to introduce a new condition into the model is quite arbitrary. I've made it that fast because that way the movies are shorter and I don't mess up the time limit on the talk. It might be more realistic if that coherence time were something like the duration of the storm, or at least a crossing time for a wave through a sufficiently large body of water, something like that. Might be an hour or more. At any rate, starting with that final rogue wave, let's advance toward a new final state. We'll zoom out so we can see the whole simulation again. And again, everything that is happening here is a combination of randomly drawn statistics and deterministic evolution. And we'll just see what happens when we reach 30 minutes. There. Do you see Aslan showing up in the waves? So even a very highly improbable outcome can be reached by this algorithm. And so what I mean to suggest is that if God really wants to, without breaking any of the statistical or cause and effect laws of the universe, it's perfectly possible for him to make a lot of interesting things happen. Maybe not any conceivable thing, but a lot of things. Things that would really give us pause. So if we try to think about how this might generalize, because I've just been talking about storm waves, imagine the number and variety of possible histories for something really big. I mean, it could be the universe, or it could be something smaller like an ecosystem, the nation's economy, the Earth's crust, the solar corona, which is my specialty. And we describe these systems statistically because we would be overwhelmed with any other approach, right? The configuration space is too large for us to comprehend. So I would argue that with or without some kind of amplification from quantum scales, we're talking about things that have some kind of unpredictable character to them. If we stipulate that in that huge variety of possible outcomes, that there are maybe 2% of things that would be just too weird, that God might not want to draw that kind of attention to himself every day, then that leaves 98% of all those imaginable possibilities that are in the domain of general providence, right? Or of special providence. So I'd argue that's a lot of freedom for divine action. So in conclusion, by realizing Polkinghorne's hypothesis in a sort of toy model world, I've attempted to address three important counter-arguments. First was the question of sufficient freedom. I'd argue there's really plenty of freedom in many of the physical systems that we inhabit in our daily lives. The amplification problem, which I argue is a non-problem because a model that does not have amplification can manifest all kinds of interesting results. And also there's the question of the implied adequacy of God's created order to fulfill his purposes. I think regarding this last point, what I have to say is that we can't view chance as a kludge by which God's will is imposed on creation. That's kind of where my simulation falls down, because I have this very linear interaction with my program as the programmer, right? So please don't picture me as doing what God does or something, right? That's not the point of this talk. But we can't view it as God versus creation. Random processes are integral to the creation. They're the way God chose to make it from the beginning. And they free the creation, in my view at least, to respond to the Creator. Consequently, perhaps general and special and extraordinary providence, which is the domain of miracles, perhaps we can envision these all integrated into an organic whole. And we need not resign ourselves to a functional deism.
A really quick, easy question, I think. What is the name of Polkinghorne's book?
1996?
There you have it.
So he's actually written about this in several books, but the one that I found most helpful was Scientists as Theologians, which was published in 1996. The reference is right there. Yeah.
So if I understood correctly, you did not have any chaos theory built into this model, is that right?
That's right. The model is not chaotic.
So if we think about something like somebody who, makes a huge fortune, say in the stock market, where chaos theory is really important, then you're really expanding by a huge degree that number of events that occur in special providence, because chaos theory gives a whole extra dimension of these kinds of events in a deterministic but not predictable way.
Yes, that's very much so. And in fact, in chaos theory, there's this thing called the Lyapunov exponent, which is, it's just a marker of the idea that this divergence or this sensitivity to initial conditions is something that expands exponentially. So it really just speeds up the time scale on which an entirely new outcome that's unpredictable based on what went before can occur. Yeah.
Thanks for an interesting talk. I wonder what you would think as a kind of a synopsis of this idea. I've heard this phrase, my God obeys the laws of physics, but totally ignores the laws of probability. It's a bit tongue-in-cheek because there's not violating laws of probability, but does that make sense?
I'm not sure I quite understood.
So I've heard this phrase kind of tongue-in-cheek, but my God obeys the laws of physics, but totally ignores the laws of probability. In other words, like when you put the lion face up there, I mean, I guess it does, there's no violation of the law of probability, right? But it's extremely improbable for the wave function to coalesce into that image.
Yeah. Well, the thing to remember about probability is that it's a matter of degree, right? I mean, we have depending on the field that we work in, okay, it may be that in your field you need a 95% confidence, let's say, or a 98% or a 99.9% confidence to get something published in a particular journal, right? So how improbable does it have to be before we regard it as, all right, this is something that can't be explained by the null hypothesis,
sure,
right?
Yeah.
And I guess, I would just point out that squishiness, right? And that's really what's at work when we talk about general versus special versus extraordinary providence. It's really going down that p-value scale.
Yeah.
You made an interesting demonstration about God working through natural processes, but it seems to me the biggest obstacle to divine providence is those difficult humans he created who tend to oppose his will, including by interfering with natural processes. So how does that affect your 98%?
Right. Well, it seems like that's a sticky wicket, right? I mean, we are if we believe that we have free will, which obviously what we mean by free will differ depending on the theological presuppositions in the room, right? Everywhere from Calvinist to Arminian and everywhere in between. But if we posit that humans also bring freedom of action into this, then there are a number of different ways to deal with it. Now, Polkinghorne favors a universe of real openness. Ultimately, anything can happen. How you then put that together with God knowing the ultimate end of things, I'm not entirely certain. There is, on the other hand, the idea of sort of the block universe, that it's like the film, right? That the whole film strip exists, and God can then reach in the middle and do the little edits if necessary. I don't much like that way of looking at it. But what if we envision it this way? Very often in physics, we solve a problem on a big grid, 2 or 3 dimensions or more, with boundary conditions where there's a relaxation that occurs, and the whole simulation all at once takes shape, so that the whole thing from beginning to end fits all of these boundary conditions that are imposed upon it. If we suppose that God allows us to apply some boundary conditions because he's given us free will, and we suppose that God also imposes boundary conditions, then the realization of this universe would then be something that happens in parallel across the entire space-time continuum, all within God's knowledge, and satisfying both his boundary conditions and the inputs that he allows us to give. That's kind of the picture that I like to hold in my mind.
All right, well, let's thank Charles once again for his presentation and answers to questions.